Newton's gravity idea? Totally good enough to get us to the moon. Ever wonder if we really get time? Like, is what we know just a tiny bit? Brian Cox's theory isn't just a thought, it's a possible way to get to the secrets of the cosmos. It could show a universe way cooler than we think. How does Brian Cox mess with what we think time is? What could that mean for how we see things? Let's check out time itself and dig into his new theory about it in the big universe. So many mysteries are out there, and some are about time and gravity. These are key to our lives. Imagine time doing weird stuff, speeding up or slowing down. And what if what keeps us on the ground isn't what we think? That's Einstein's relativity stuff. Time and gravity get all strange. Albert Einstein gave us a fresh look at the universe with his relativity ideas. He taught us how time acts in crazy situations, like going super fast. It all started in the early 1900s when Einstein had two big ideas, special and general relativity. Special relativity, from 1905, flipped our view of time and space. Plainly, the rules of physics. Same for everyone who isn't speeding up. This theory says cool stuff can happen, like time slowing down at certain speeds. Think of a light clock to get it. You're in a fast spaceship. A light beam bounces between mirrors. Light speed is the same for everyone. So, light goes a longer path. But the time for the light should be the same inside and outside the ship. Because of the longer path, it looks like it takes more time for the outside person. That time difference is time slowing down. Time changes based on how you move. Knowing how things change when moving fast, relativistic stuff, isn't just school stuff. Scientists use machines to make particles zoom. We gotta think about time in a new way to get good results. Einstein's special relativity, 1905, changed how we see time and movement. It says physics rules are the same for everyone, even if moving. Events that seem at the same time for us might not be for light-speed travelers. Another thing, length shrinks. If moving, stuff looks shorter from where you're standing. E equals mc caret superscript 2. That's energy and mass turning into each other. Big for tiny particles going super fast and when atoms break up in nuclear reactions. IRL, special relativity is in GPS. Satellites send signals. They move, so time acts different. We have to think about this time change or GPS goes wrong. Special relativity says time isn't set, it depends on movement. It's like our normal idea of the universe is off. Time isn't fixed, motion changes it. Some ideas, like light speed being the same and energy/mass links are proven. But there's more with Einstein's general relativity, 1915. It's all about gravity and how the universe is made. Gravity isn't just a force. Space and time are bent. Gravity? Not magic. Just how things move. Brian's take. Think of the universe as 4D, space and time. Big stuff shapes space and time around them. That shape? That's gravity. Like a stretched blanket, heavy stuff makes a dent. Smaller things roll into it. Gravity's not a force, it's space bending. General relativity says how stuff moves in the solar system. Planets circle the sun. It plots paths, like Earth's oval orbit. Brian says it's better than the old gravity pulls idea. Space and time are bendy. Makes sense. A big moment for general relativity. 1919 solar eclipse. Arthur Eddington watched how starlight bent near the sun. The sun's mass should bend starlight. And it did. Einstein was right. Like motion can change time in special relativity, gravity also changes time. Strong gravity. Time moves slower. Near a black hole. Your clock ticks slower versus far away. General relativity gave us black holes, crazy gravity zones. Inside, gravity is so strong, even light can't escape. The edge? Event horizon. Cross it, you're gone. Einstein's general relativity. Big for the universe. First, he added a cosmological constant because he thought the universe was still. When we found it expands, he said it was a mistake. An expanding universe is from the Big Bang theory. Another thing from general relativity. Gravitational waves. Ripples in space and time when big things move fast like black holes merging. 2015. Scientists at LIGO found gravitational waves. Einstein was right again. Over time, tests proved general relativity true. How planets move, starlight bends, gravitational waves. General relativity is solid. Saying gravity is a lie might sound weird. But in physics, it's normal to talk about different ideas. Scientists like Brian ask, what if? One idea that messes with gravity? Modified Newtonian dynamics, MOND. It says gravity acts different at slow speeds in galaxies. No dark matter needed. MOND says gravity gets stronger at low speeds. The gravity talk also has dark matter and dark energy to kinda explain stuff in space. Some say we don't need these and other ideas can do the job. Some scientists look at new ideas, like unknown particles or forces that can change gravity. Important thing, science tests everything. Einstein's 4D time idea, where time travel is limited by light speed, is thought about with wormholes and shortcuts. Stephen Hawking said time travel is hard. Experiments see if new theories explain gravity and match what we know. Even though folks talk about other ideas, nothing really beats the known rules of gravity. Challenging ideas help science move forward. General relativity is still the most important one. Despite different ideas, it passes tests, explains how planets move, light bends. General relativity is strong. Because it is simple and encompasses a wide range of phenomena. Like special relativity says time changes based on movement. Let's see how that hits real-life scenarios like space travel. Space travel is cool, distances are long. Einstein said light speed is the limit. It's hard to travel between stars, even with great tech. Get this, the twin paradox. One twin stays on Earth, the other zooms to a far star. The space twin is younger when they return. They went to the future. Time matters for space trips. The longer you go, the more time slows. Astronauts visiting close stars would age slower than folks back home. It sounds like science fiction, but it's the real thing. Say we sent a crew to a star system. The distance means the trip takes years. Space travelers would feel time shorter because time slows down for them. Lots of time passes on Earth. Time messes not just with people but tech. Computers and devices need to think about time slowdown for good results. Space trips at high speeds have issues, being alone, radiation, and missing Earth. We see time changes every day in GPS. GPS uses timing from signals. Because these satellites move, time acts different. We must think about this. Otherwise GPS goes wrong. So, special relativity teaches us that time isn't the same for everything and everywhere. It depends on how things are moving, and this idea challenges what we usually think about time and space flow in one only direction from the past into the future. Entropy describes this trend, a way of things losing order. The second law of thermodynamics demonstrates that entropy tends to increase with time. Things often get more scattered or chaotic. Picture a deck of cards going from orderly to jumbled when shuffled. There are mysteries all around us, and some have to do with time and gravity, basic parts of our world. What if time wasn't steady? What if it sped up and slowed down? What if gravity wasn't what it seemed? That's what Albert Einstein's theories of relativity suggest, a weird take on time and gravity. Einstein gave us a way to see the universe differently. His work is the base for understanding how time works in different situations, like when you're moving super fast. It kicked off in the early 1900s when Einstein came up with two ideas, special and general relativity. Special relativity, from 1905, flipped our view of time and space. Simply put, the rules of physics are the same for everyone who isn't speeding up, no matter how they move. This brings up ideas like time slowing down under certain conditions. One way to get your head around this is the light clock idea. Picture yourself in a spaceship zooming super fast, close to light speed. There's a beam of light bouncing between two mirrors. Because light speed is the same for everyone, the light beam seems to travel a longer path. For the person outside the ship, it looks like the light takes longer to travel that path. Einstein called this time difference time slowing down. Time changes depending on how you're moving. Understanding how things change at high speeds, also known as relativistic consequences, isn't just theory. Scientists use machines like the Large Hadron Collider to make particles move crazy fast. When that happens, we have to think differently about time to get our data right. Einstein's special relativity came out in 1905, switching up how we see the universe, mostly about time and speed. It messes with what we think is normal. It says physics rules are the same for everyone, even if they're moving. Usually, we think if something's moving and we speed it up, it goes faster. Einstein said there's a speed limit, light speed. Plus, events that seem to happen at the same time for us might not for those moving close to light speed. Another idea is length contraction. If something's moving, it looks shorter when viewed from a still spot. Then there's E equals mc caret superscript 2, showing energy and mass can swap. This is key for understanding fast-moving particles and stuff like atom splitting. Special relativity matters daily, like with GPS. GPS satellites send signals to your device while moving. Because of their movement, time changes a bit for them. If we didn't consider this time change, your GPS would be way off. Special relativity says time isn't the same everywhere, it depends on movement. It's like our usual view of the universe is a little off. Time isn't set, it's affected by motion. Ideas like constant light speed and the link between energy and mass have been proven. But there's more, like Einstein's general relativity from 1915. This gets into gravity and the shape of the universe. It changes the idea that gravity just pulls things. Instead, space and time are curved. It's like saying gravity isn't a force, but how things move in the universe. Brian's view is that general relativity means the universe is four-dimensional, with 3 space dimensions and 1 time. Big stuff like stars affects how space and time are shaped. That shaping is what we call gravity. Space-time is like a stretchy blanket. Put something heavy like Earth on it, and it makes a dent. Place a smaller ball near Earth, and it rolls toward the dent. That's how objects act because of gravity, not a force, but a reaction to space-time bending. General relativity explains how things move in our solar system, like planets orbiting the Sun. It can tell us where the planets will go, like Earth's oval orbit. Brian says this differs from gravity just pulling things. The curved space and time idea fits what we see better. A big moment for general relativity was a solar eclipse in 1919. Arthur Eddington led a team to watch how light from stars bent around the Sun. The theory was that the Sun's mass would curve the starlight. The eclipse showed that Einstein was right. Plus, motion changes how we feel time, according to special relativity. Gravity also affects time. Stronger gravity makes time move slower. A clock near a black hole would tick slower than one far away. General relativity brings up black holes, spots with crazy gravity. Not even light can escape a black hole. The edge is called the event horizon. Once you cross it, there's no return. Einstein's general relativity impacts how the universe is set up. He added a cosmological constant because he thought the universe was static. When we found out it was growing, he called it a mistake. The expanding universe idea, based on general relativity, is a key part of the Big Bang theory. Another idea is gravitational waves, ripples in space and time caused by big, fast-moving stuff, like black holes merging. In 2015, scientists at LIGO spotted gravitational waves, proving another part of Einstein's theory. Over time, scientists have checked general relativity, and it's held up every time, from planet movement to starlight bending to gravitational waves. Saying gravity is a lie might sound wild because we feel it all the time. But in physics, it's normal to talk about different ideas. Scientists question gravity. One idea, modified Newtonian dynamics, MIND, says gravity acts differently at slow speeds in galaxies, without needing dark matter. Rather than adding invisible matter, mine says gravity gets stronger at low speeds.